stating the general objectives. So first, analyze and present the mathematical structure of number patterns. Second, relate patterns to practical application in mathematics, science, and daily life. Third, encourage critical thinking and creativity in identifying and explaining patterns. So here are the objectives for arithmetic sequence topic. So first, define an arithmetic sequence and identify its properties. Second, derive and apply the formula for the nth term and sum of an arithmetic sequence. Third, solve real-life problems involving arithmetic sequences. So what is arithmetic sequence? An arithmetic sequence is a sequence of numbers in which the difference between consecutive terms is constant. This constant difference is called the common difference. As you can see in the screen, that is the general form of an arithmetic sequence.
So good day everyone, my name is Chamela Flantaya and I will be giving you an example of arithmetic sequence. So take a look at this number or the number sequence. This numbers has a constant or common difference which is we can get if we follow the formula on the next slide. So as you can see on the screen, D equals A2 minus A1 is the formula that we will use to get the consecutive term or common difference. But before that, we should label first the number sequence that I have shown you earlier. So A1 is denoted by 4, A2 is denoted by 11, A3 is denoted by 18, and lastly, A4 is denoted by 25. We will use those given numbers to solve for our arithmetic sequence later on. So now let's solve for our consecutive term. So D equals A2, which is denoted by 11, minus A1, which is denoted by number 4. So 11 minus 4 is equal 7. So our consecutive term for the number 4, 11, 18, and 25 is 7. So here's our given numbers, which will we use to create a situational problem and will solve using an arithmetic formula. So here's the situational problem that we have created using the given numbers that I have shown on you on the previous slide. So an auditorium has 4 seats in the first row, 11 seats on the second row, 18 seats on the third row, 25 seats on the fourth row, and so on, and has 9 rows of seats. So here's the guide question based on the situational problem that we have created earlier. So the first question is, what is the ninth term of 4, 11, 18, and 25? The second one is, how many seats are there in the ninth row? So we will be getting the answer after we have solved it. So an equals a1 plus n minus 1 times d is the formula for an arithmetic sequence. So an is denoted by a9, which is what we are looking for. A1 is denoted by 4, n is denoted by 9 again. And then D is denoted by 7, which is our consecutive term or our common difference. Since we have now our equation, we're now going to solve for our ninth term. So the first thing that we will be solving is the one that is in the parenthesis, and then the second one is the multiplication, and the third and last one is the addition. So 9 minus 1 is equals to 8, and 8 times 7 is equals to 56, and 4 plus 56 is equals to 60. So our A9 or the ninth term is equals to 60. So you can manually check the result by adding 7 to the following denoted numbers. As you can see on the screen, A9 is 60. So the ninth row is equals to 60. So to answer our guide question earlier, the ninth term of 4, 11, 18, and 25 is 60, and there are 60 seats in the ninth row. So I hope you learned something, and that's it for arithmetic sequence.
The Fibonacci sequence, the following numbers make up the Fibonacci sequence, such as the given 0, 1, 1, 2, 3, 5, 8, 13, and so on. So please remember always that it starts from 0 and 1 usually. And lastly, take note that the numbers in the Fibonacci sequence are also called Fibonacci numbers. So to get the given is that the two numbers are added up to determine the next number. So for example, is that 0 plus 1 is equals to 1, 1 plus 1 is equals to 2, 2 plus 1 is equals to 3, 2 plus 3 is equals to 5, 3 plus 5 is equals to 8, 8 plus 5 is equals to 13, and so on.
The Fibonacci sequence formula, it deals with the Fibonacci sequence finding its missing terms. Fibonacci formula is given as f sub n is equal to f sub n minus 1 plus f sub n minus 2. Fibonacci sequence of numbers, f sub n, it is defined using the recursive relation with the seed values of f sub 0 is equal to 0 and f sub 1 is equal to 1. And there are two sequence of different using parts, such as the kick-off and the recursive relation. Kick-off part is f sub 0 is equal to 0 and f sub 1 is equal to 1, while the recursive relation part is f sub n is equal to f sub n minus 1 plus f sub n minus 2.
First example is, find the 10th term of the sequence 1, 3, 4, 7, 11, 18, and 29, and 47. So here is how to solve it. So first term is 1, and the second term is 2. So we simply added the two terms to form a third terms. So that is 4. So the second term and the third term is we add them to form a fourth term. Then we add them third term to fourth term to form a fifth term. Eighth term. So 29 and 47 add them to form a ninth term. It's 78. Sorry guys. So 47 and 78 we add them to form a tenth term. Tenth term is 123. So our tenth term is 123. So the answer of this one sample is 123.
My name is Satori Magallanes and I'm from Group 1. So what is fractal? In a simple word, fractal is a complex geometric shapes that exhibit cell similarity, meaning it can be divided into the part that resemble the whole at scales. So meaning to say repeatedly or cell similarity, meaning it can be divided into many parts. So where it came from? Benoit Mandelbrot was discovered fractals during 1985, and Benoit was born in 1924 and he died in 2010.
Fractals can be found in nature. One of the great examples of this are trees because of how they grow and how they branch out. So as you can see in the picture, if you look at a bigger branch and compare it to a small branch of a tree, you will notice that they have the same shape. You can keep zooming in and still you will find the same branching pattern. That's the key characteristics of fractals, wherein there is a similar pattern to a different sizes. Each smaller section looks like a tiny version of the bigger part of a branch, and that is fractals.
In conclusion, fractals are everywhere. In nature, like river networks and coastlines. In science, like lung tissues and brain structures. And even in technology, like designing antennas and computer graphics. They're essentials for understanding complexities in natural and artificial systems.